Welcome back to Prep for FE. Today, we are dissecting the NCEES Handbook rules for significant figures. The calculator on the left side produces raw arithmetic, an infinite, unconstrained decimal string. But the engineering blueprint on the right side requires the data to be constrained by physical precision. Significant figures are a strict mathematical protocol. In any operation, the number of digits you retain determines the reported accuracy of your result. The NCEES framework uses these figures to track the certainty of measured data as it moves through complex calculations, ensuring the output never claims more precision than the input supports. To maintain this data integrity from initial input to final engineering solution, the handbook dictates 6 specific rules. On the FE exam, the multiple choice options are designed to test your application of these rules. Selecting the unrounded output from your calculator is a common trap that leads to the wrong answer. The protocol begins with identifying which digits are significant based on their value and position. Rule 1 states that non-zero digits are always significant. In this 5-digit number, every integer from 1 through 9 represents a verified measurement. Because these digits represent physical quantities, there is no ambiguity regarding their precision. The complexity arises with the number 0, which can serve as either a measurement or a placeholder. Rule 2 addresses this. Any zeros sandwiched between 2 significant digits are captured and become significant themselves. This capture rule applies regardless of how many zeros are positioned between the non-zero digits. The internal structure dictates the certainty. If the outer bounds of a number are verified, every digit within those bounds is treated as certain. When moving to decimal values, the absolute value of the number changes the significance of the zeros. Rule 3a specifies, for numbers less than 1, zeros to the right of the first non-zero digit are significant. Here, leading zeros are strictly positional placeholders. However, the trailing zero is significant, recorded to indicate a specific level of decimal precision. The requirement changes for values that include a whole number component. Rule 3b states that in the decimal portion of a number whose absolute value is greater than or equal to 1, all zeros are significant. The presence of the whole number 1 activates the significance of every subsequent digit in the sequence. Comparing these two values show how the leading zeros shift from placeholders to significant measurements based on the presence of an integer. An integer anchors the decimal precision, changing the zero's role from a placeholder into a specifically measured value. After identifying the digits, you must apply them to calculations, where the input precision limits the output. Rule 4 applies to addition and subtraction. The input with the least significant digits after the decimal dictates how many digits follow the decimal in the result. Here, 4.2 has the shortest decimal tail, with only 1 digit after the point. That tail creates a vertical cutoff. The sum is truncated at this column, so the answer doesn't claim more precision than the weakest input. The second half of Rule 4 focuses on the left side. The input with the most significant digits left of the decimal dictates the result. Here, 12.11 has the largest whole number block. That constraint carries down, maintaining the structure. In addition and subtraction, data integrity is bound by vertical alignment. This prevents the result from appearing more precise than the least certain measurement. Multiplication and division operate differently, shifting the focus from vertical alignment to the total count of significant digits. Rule 5 states that the result of multiplication or division has the same number of significant digits as the input number with the least total count. The factor 1.2 has only 2 significant digits, making it the limiting variable. Although the raw product is 5.472, it must be rounded to 5.5 to match the 2-digit limit of the input. While Rules 4 and 5 govern individual operations, Engineering Custom dictates how you report a final solution. Rule 6 states that in engineering problems, it is customary to retain 3 to 4 significant digits in the final result. This standard is applied once all calculations are complete to standardize the final documented answer. Rule 6 ensures that calculations do not suggest a level of practical accuracy that the physical data cannot support. These 6 rules form a systematic workflow for every calculation on the FE exam. Rules 1, 2, and 3 comprise the identification phase, defining which digits are structurally sound before the math begins. Rules 4 and 5 manage the operational phase, restricting the output based on addition, subtraction, multiplication, or division. Rule 6 provides the final delivery phase, applying the 3 to 4 digit standard to the final result. Many multiple choice options on the exam are based on common rounding errors or the failure to identify placeholders. To find the correct answer, you must filter every calculator output through this NCEES rule set. Applying this strict protocol consistently ensures that your final results accurately reflect the physical limits of the measured data.
Today, we're going to learn significant figures in detail. We'll go through the rules, solve 2 sample problems, and then you'll try one with the answer key. Let's begin. Significant figures are the digits in a number that carry meaning about precision. In other words, they tell us how accurate a measurement is. Let's list the rules one by one. Rule 1, non-zero digits are always significant. Rule 2, any zeros between 2 significant digits are significant. Rule 3a, in numbers less than 1, zeros to the right of the first non-zero digit are significant. Rule 3b, in numbers greater than or equal to 1, all zeros in the decimal portion are significant. Rule 4, for addition and subtraction, the number with the fewest digits after the decimal point controls the rounding. Rule 5, for multiplication and division, the result has the same number of significant figures as the input with the least significant figures. Rule 6, in engineering, it is common to keep 3 to 4 significant figures in the final result. Now let's do example 1. Count the significant figures in the number 0.00450. We will highlight the digits that count. The first non-zero digit is the 4, so zeros before it are not significant. The digits 4, 5, and the trailing 0 are significant because the number is less than 1 and the 0 is to the right of the first non-zero digit. So this number has 3 significant figures. Example 2, multiply 12.3 times 0.54. First, count significant figures in each number. 12.3 has 3 significant figures and 0.54 has 2 significant figures. So the answer must have 2 significant figures. Now compute the product. 12.3 times 0.54 equals 6.642. Rounded to 2 significant figures, the answer is 6.6. Now you try one. Add the numbers 15.62, 3.1, and 0.018. Remember, for addition, round to the least number of decimal places. Pause the video and solve it. Let's check the answer. First add them to get 18.738. The least decimal places is 1 because of 3.1. So we round to 1 decimal place. The final answer is 18.7. Quick recap. Non-zero digits are significant. Zeros between significant digits are significant, and the rounding rule depends on the operation. Multiplication and division use the least significant figures. Addition and subtraction use the least decimal places. Keep 3 to 4 significant figures for engineering results. That's the key idea.